Here we are in the last section of chapter 21. This was a very long chapter, but it covered a lot of important information. And even with that, please don't think that we are done talking about derivatives, because we are not. But this is at least the last section in this chapter. It's implicit differentiation. And you would use implicit differentiation whenever you have a function that can't be written as x equals something or y equals something. Okay, where you can't solve for one variable like y. All right, up until now, that's what we've had. We've had a function that was y equals something or v equals something, and we were able to just deal with the x's and no other variable. But that doesn't always happen. So what we're going to do, it's just a little extra step that you have to remember when you're doing implicit differentiation. You're going to take the derivative normally, and there may be x's that you take the derivative of and y's that you take the derivative of. But there's one small thing. Whenever you take the derivative of something that has y in it, and whenever you're taking the derivative of the y part of that, you would have to write the word dy dx afterwards. All right? And then, so you're going to have some terms, and some of them will have dy dx in them and some won't, and you will solve that resulting equation for dy dx. So the best way to do this is with an example. All right, and there's kind of a funky equation. I really can't solve that so that it says x equals something in terms of y, and I can't solve it so that it says y equals something in terms of x, so I have to use implicit differentiation. So here I go. If I take the derivative of the first term, that's x, and the derivative of that is 1. Now looking at the second term, x squared y, I've got to use product rule there, and here's the split. Okay? So the derivative of x squared is 2x times y. Now notice that I didn't actually take the derivative of the y part, so I don't write dy dx just yet. All right, so the derivative of x squared is 2x, y stays as y, and now I do the second part of that. X squared stays x squared, and now I'm going to take the derivative of y, which would be 1, and then since it is the derivative of the y part of this term, I'm going to write dy dx. All right. And then I move on to the last term. Nothing crazy here. The derivative of y cubed is 3y squared, but since I took the derivative of the y part of something, then I've just got to write dy dx after it. And then the derivative of 100 is 0. Okay, so all of that is how I get all of those terms. And this was as a result of the product rule. So there's my derivative. What I'm going to do now is, since I'm solving for dy dx, I'm going to move every term that has dy dx in it on the left, which they already are, and then any term that doesn't have dy dx in it, I'm going to move that to the right. So that's the 1 and the 2xy, which will of course change sign when I move them to the right. So now that everything on the left has a dy dx in it, I'm going to factor out the dy dx, and that's what I get. And the right hand side stays the same, so if I'm solving for dy dx, I'm just going to divide by these parentheses here. And so that's what I get. Negative 1 minus 2xy all over x squared plus 3y squared. All right. So as an example, let's hide this a little bit. We are going to find the gradient of the tangent to the curve x squared plus y cubed equals 5 at the point where x equals 2. All right, well, first let me notice that when x equals 2, this term is 2 squared, which is 4. So 4 plus y cubed would have to equal 5, meaning that y cubed is 1, meaning that y is 1. So it's always a good idea to solve for y before you proceed, because very often x and y show up in your derivative dy dx function. All right, so this is what I'm taking the derivative of. X squared plus y cubed equals 5. The derivative of x squared is 2x. The derivative of y cubed is 3y squared. And since I took the derivative of the y part of something, I have to write dy dx. And the derivative of 5 is 0. And if I solve that, I get dy dx equals negative 2x plus, or negative 2x over 3y squared. All right, and at this specific point, I'm just going to plug in x equals 2 and y equals 1, so I get negative 2 times 2 over 3 times 1 squared, which is negative 4/3. And so that's how you would do that. All right, we will do more examples of this tomorrow, and in the meantime, ask me questions if you want to by Facebook or by email.